Picture a snowball from another star barreling into our neighborhood, gliding past the inner planets like a tourist doing a whirlwind city tour. That is 3IATLAS, an interstellar comet that does not belong to our solar family. And right now, all maps point to a close pass near the orbit of Mars. Why Mars? Why now? And what invisible hands are tugging on this visitor's path? Buckle up. Space is about to get very cause and effect, with a side of cosmic gossip. Earth is basically a rock that won the cosmic lottery. Tonight, we peek at the raffle drum that brought our guest to town. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly with a cup of tea and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Imagine you are standing on a quiet beach at night. The horizon is a black ribbon, the sky above is loaded with cold diamonds, and then a single spark tears across the darkness. A traveler who did not get the memo about slowing down. That is the feeling astronomers get when a truly alien comet shows up. It is not just a new object, it is a new origin story. Most comets are local celebrities from the deep freeze beyond Neptune, but this one is the out-of-towner who speaks fluent vacuum and carries souvenirs from a star we have never met. If the solar system had a guest book, this signature would be written in mysterious handwriting with a pen that smells like ancient ice. So why are we so excited about a path that brushes the lane of Mars? Because the cosmos does not throw random parties. Every near pass is a headline about timing, a footnote about history, and a teaser about destiny. When a traveler from another sun happens to cruise the neighborhood of the red planet, that is a cosmic coincidence with plot potential. It is not that Mars texted the comet and said, "Meet me curbside." It is that the stage has been set for a close-up, and the lighting crew, also known as the sun, just dimmed the house lights and raised the spot. Before we get tangled in the how, let us savor the thrill of the what. We are watching a messenger that formed under a different recipe. The grains in its crust were heated and cooled by a foreign fireplace, stirred by a different rhythm of seasons, and glued together by ancient frost that has been hiding its secrets since before our own planets grew their first crusts. It is like cracking open a time capsule and finding a mix of artifacts that feel familiar but smell faintly of another country's rain. That scent is curiosity's favorite flavor. Scientists live for this stuff. Space fans too. Honestly, even your neighbor who swears they are not into astronomy might look up if you tell them a visitor from another star is waving at Mars. Now, let us talk human. Whenever we point to the sky and ask, why is that thing going there? We are really asking a couple of sneaky questions. First, what rules is it obeying? Second, what story is it telling? The rules are the quiet kind, written into the deep fabric of space. They do not shout, but they never stop. The story is the noisy kind we tell ourselves to make sense of a scene we did not direct. That is okay. Narratives are how our brains hold on to cosmic spaghetti without dropping the plate. Think of this chapter as the plate. We are not slurping the noodles yet. We are admiring the shine. Interstellar visitors also poke at a bigger feeling, home. We like knowing what is ours. The solar system is our cosmic backyard, full of familiar lawn furniture and that one slightly dented barbecue named Mercury. When a stranger wanders in, we suddenly notice details we ignored. The tilt of planetary paths, the hush between the planets where dust drifts like ash. The fact that Mars, our rusty neighbor, has the stage presence of a retired rock star who still pulls a crowd. The visitor sharpens our eyes, even if it lingers only briefly. It changes the way we see our own porch light. And yes, I hear you. Why Mars, though? The short answer for now is that arrivals and avenues sometimes line up in dramatic ways. Picture a parade that turns the corner just as your best friend steps onto the balcony. Was the parade planned around them? Probably not, but the timing still makes for an unforgettable selfie. The Mars moment has that vibe. It is the sort of cosmic, almost meet-cute, that makes mission planners stare at whiteboards and whisper, "Could we catch a glimpse from there?" It also makes poets on Earth write lines they will later pretend are not about a snowball. There is a second reason this pass is delicious. Vantage. When something skims a planet's neighborhood, the planet becomes a camera tripod with front row seating. Observers on and around Mars, if they have the right lenses and a clear look, can see the visitor from an angle we do not get from Earth. That is like watching a magic trick from the wings instead of the audience. You glimpse the way the scarf moves, the way the hand flicks, the way the smoke curls. You do not spoil the magic. You learn to love it more. While we are in Hook territory, let us sprinkle a few tasty what-ifs without biting into the main course. What if interstellar travelers are more common than we think? A quiet reign of tiny ambassadors that we only sometimes notice when one turns shiny. What if a fraction of the chemistry that primed planets for life arrived not by local delivery, but by long-haul courier, stamped by foreign suns? What if every system exchanges postcards of dust across the Gulf, a galaxy-wide pen pal club where the stationery is frozen and the ink is starlight? These are not claims, they are doorways, and doorways are where stories begin. Humor break, because curiosity loves a chuckle. Space is vast, but it is also petty in funny ways. Planets bicker over orbits like siblings sharing a backseat. Moons rehearse their tides like bands doing sound check. And comets? Comets are the universe's food trucks. They roll in, leave a trail of crumbs, and everyone tells a friend to come outside. Photosynthesis may be plants saying they invented solar panels first, but comets are the cosmos saying snacks are on the way. Please bring mittens. Here is the promise of this series. We will not rush. Each chapter will peel one layer of the onion and let your eyes water in a good way. No jargon, fireworks, no alphabet soup, just clear ideas and crisp images that let you feel how a single icy traveler can connect our local story to a larger map. By the end, you will not only know what is drawing 3IATLAS toward the lane of Mars, you will also feel why that matters to anyone who has ever looked up and felt small in the best possible way. Stay with me. In the next chapter, we will properly meet the visitor, explore what makes an interstellar comet different from our homegrown crowd, and unpack why its accent matters to the grand conversation about where worlds come from. Chapter 2. Meet the visitor. Interstellar objects do not loop the sun. They fly in on open, hyperbolic paths and keep going. Think road trip, not round trip. 3IATLAS is just the third such traveler ever confirmed. It carries ices and dust that formed under a different stellar lamp, a time capsule with a passport stamp from somewhere else in the galaxy. If comets are dirty snowballs, this one is a dirty snowball with a mysterious accent. So what does it actually mean to arrive on an open path? Imagine a racetrack where almost every runner is bound to keep circling, lap after lap. Then a stranger sprints in from the parking lot, cuts across the infield, and exits through the far gate without ever touching the track again. That is the geometry of a hyperbolic visitor. Its speed is above the local escape threshold, and its path bends only once before it is gone. There is no membership card, no return ticket, only a graceful detour through our neighborhood. Astronomers can tell this from the way the object's course plots against the sky, night after night. The curve refuses to close. It is the cosmic equivalent of a signature that does not fit on the line. How do we even catch a stranger like this in the act? The sky is big and interstellar travelers are small. The answer is patience plus automation. Survey telescopes sweep large swaths of darkness every clear night, comparing fresh images with last night's starfield. When something moves against the background, the software flags it, a bit like your photo app, noticing a new face in a crowd. Most flagged objects turn out to be familiar residents, near-Earth asteroids, long-period comets, the usual suspects. Every so often, the data whisper, this one is different. The motion is too fast, the path too open, the timing too odd. That is when the phone tree lights up. Amateur and professional observers pivot, and a quiet speck becomes the headline of the week. Space paparazzi, assemble. Now to the personality of a visitor forged under a foreign sun. The building blocks in its ice were not assembled in our backyard. The grains of dust likely grew in a cloud with a different mix of elements under a furnace that may have burned hotter or cooler than ours, with shock waves and radiation that left their own fingerprints. Picture ice that has spent ages marinating in cosmic rays, simmering slowly in the deep freezer of interstellar space. That long marinade can split molecules, shuffle bonds, and darken surfaces into a baked crust called a mantle. Beneath that crust, fresher ice waits like a reserve battery. When the object approaches warm light, vents can open, gas escapes, and a halo of vapor and dust inflates around the nucleus. In comet speak, that halo is the coma. In human speak, that is the moment the quiet tourist starts waving. Compared with comets raised in our distant cloud of origin, an interstellar one might carry unusual ingredients or unusual ratios of familiar ingredients. Think spices we know, but in a recipe we have never tasted. Traces of carbon monoxide or carbon dioxide might be stronger or weaker than we expect. Exotic organics could hitchhike in the dust, complex carbon chains that formed in the cold between stars. That does not mean life. It means the pantry of chemistry is generous, and the cosmos is very good at slow cooking. If you have ever left a tea bag in water for an afternoon and returned to a brew that could power a small airplane, you know what long steep times can do. Interstellar space offers steep times that make patience look impulsive. What about size and shape? Most visitors are small because small things are easier to toss out of young planetary systems. Imagine a baby solar system as a rowdy nursery full of newborn planets playing gravitational bumper cars. Leftover rocks and icy clumps get flung everywhere. A fraction of those clumps are launched so hard that they leave home entirely. Over the ages, some will wander close to other stars and show up in someone else's sky, which is how we meet our guest. The nucleus itself is likely modest, a lumpy peanut or a knobbly potato rather than a perfect sphere. Rotation can be steady or chaotic, a slow spin or a tumble, depending on past nudges. The surface may be darker than a parking lot at midnight because dust skins built by eons of radiation tend to hide shiny ice. Space is a champion at making things look stealthy. You may wonder whether this traveler will behave like the comets we are used to. The bright tail, the soft glow, the photogenic drama. That depends on how much gas is trapped in the ice and how easily it escapes. Some interstellar objects seem reluctant to puff. Others shed material with theatrical timing. Outgassing is not just decoration. Jets can act like tiny thrusters, changing the spin or the path in subtle ways. For observers, those changes are treasure because they help reveal the shape, the vent locations, and even the grain size of the dust. It is a bit like reading a diary written in steam. Color also tells a story, measured with filters. Many comets lean slightly toward red, a hint from organic-rich dust and weathered crust. Interstellar travelers can show similar tints or surprise us with palette shifts. A rosy tone might suggest a long history of irradiation. A more neutral shade can hint at fresher surfaces or unusual composition. No need to memorize the hues. Just know that astronomers can translate color into chemistry, the way a barista translates aroma into beans and roast. What about the accent in this snowball's voice, the thing that makes it unmistakably not from here? It is in the details, the exact curve of the incoming path, the speed long before it felt much warmth, the early spectrum lines that do not quite match our local patterns, the timing of how the coma breathes as light increases. Each clue is small on its own, but together they whisper elsewhere. That single word can rearrange how we think about planet formation, because if one stranger arrives, more exist. And if more exist, then the exchange of raw materials between star systems is not rare drama, it is background traffic. The galaxy might be running a quiet postal service, and we are finally checking the mailbox. Let us end this meet and greet with a human-scale image. Imagine a traveler stepping off a long train with frost on their coat and sand in their shoes, carrying a suitcase stamped with unfamiliar stickers. They smile, tip the hat, and keep walking. You do not know their language yet, but you recognize the meaning. There are other towns, other kitchens, other mornings. 3IATLAS is that traveler. Our job is to listen carefully while it passes. Next, we will turn our ears toward the loudest voice in the room that bends every path it sees, and we will let it explain why straight lines are rare in a curved universe. Chapter 3. The main tug. The number one force drawing anything in the inner solar system is the gravity of the sun. Full stop. The sun is the heavyweight champion. Everything else is supporting cast. 3IATLAS is not specifically aiming for Mars, as much as it is falling past the sun, while Mars happens to be in the neighborhood. Gravity is not a tractor beam with opinions, it is a curve in space that everything follows. Black holes might be the universe, saying delete browsing history permanently. The sun is the universe, saying please mind the curvature. To understand why the sun calls the tune, picture space as a flexible floor. Put a bright, massive lamp in the middle, and the floor sags into a wide bowl. Roll a marble across that bowl, and its path bends. Not because the marble likes the lamp, but because the floor tells it how to move. That bowl is the sun's gravity well. The deeper the bowl, the more the path curls. A visiting object like 3IATLAS is a marble that was already moving fast when it reached the rim. It does not settle into a lazy loop. It skims the bowl, swoops near the center, and then climbs back out. Still moving, still free, just redirected and energized by the downhill sprint. This flow has a rhythm built from two ideas, energy and direction. Energy decides how deep into the bowl the traveler can dive and still climb out. Direction sets the shape of the curve, the way the path leans and twists as it falls. Together, they define a one-time encounter with the sun's pull. If the visitor's energy is high enough, no matter how close it sweeps, it will not be trapped. It will leave with a story about a close brush with a star and a slightly new heading written into its future. Think of gravity here as the ultimate stage designer. It does not shove, it sculpts. The sun reshapes the geometry around it so that straight lines are not truly straight. Objects believe they are going as straight as possible, but the floor they are walking on is curved, and so their honesty becomes an arc. This is why the phrase falling past the sun is a better picture than words like pulled or yanked. The visitor is simply following the shortest, most natural route in a landscape we cannot see, but can calculate, and more satisfyingly, feel through outcomes. As 3IATLAS approaches the deep part of the bowl, its speed grows. That increase is not a mysterious push. It is the conversion of altitude in the gravity well into motion. The closer the path runs to the center, the more the traveler trades stored fall for speed. Then, having swung through the lowest part, it climbs the far slope, losing speed again as the stored fall turns back into altitude. The overall trade balances if the traveler does not shed material or change its spin in a way that matters. The sun is strict but fair. What you bring in, you take out, only with your direction, edited like a sentence rewritten by a picky teacher. There is also the matter of the closest approach, the moment of nearest sun distance. At that point, the bending is most dramatic. Imagine a roller coaster darting through a canyon where the track curves so tightly that your stomach briefly files a complaint. The path before and after this point can look almost mirror symmetric, but the mirror is tilted. The angle by which the trajectory swings is set by how near the visitor threads the center and how fast it is moving when it arrives. Miss the inner spotlight by a wide berth and your path gently bows. Graze the spotlight, and the arc snaps like a sharp elbow turn. Either way, the sun's bowl writes the choreography. You can also feel the sun's dominance by considering what does not matter much in this chapter. The background drag of thin gas is negligible out there. Magnetic fields knit beautiful patterns in charged particles, but a solid body with little charge is not tossed around like a leaf in a stream. Light itself does not push a chunky nucleus very hard. The chief sculptor remains the central mass, steady and overwhelming. If the solar system were an office, the sun would be the boss, whose calendar is everyone's calendar, and all other influences would be sticky notes that sometimes help, sometimes annoy, but never cancel the meeting. Another way to taste this dominance is to imagine freezing time and drawing arrows showing the direction a free traveler would move at each point in space. Near the sun, the arrows are steeply tilted inward, like rain blown toward a drain. Farther away, they flatten, almost straight, almost free. Our visitor drifts from the flatter plane into the tilted region, slides through the steepest part, and escapes back to the flatter far field. The change from almost straight to strongly curved and back again is the signature of a grazing encounter with a central monarch. The sun's authority also sets the tempo of the visitor's encounter. There is an approach phase when the path is only slightly bowed, then a rush of acceleration as the traveler dips deep, and finally a long exhale on the way out. Observers time their watches to this tempo. Early on, small adjustments in measured position tell us the far field speed and direction. Near closest approach, rapid changes in brightness and position give us the sprint statistics. Afterward, the slowing drift lets us refine the final heading. It is like watching a bird ride a thermal, gentle glide, sudden swoop, smooth climb, and because gravity is geometry and not malice, there is a strange comfort here. The same rule that keeps planets circling without a leash also allows a stranger to visit and depart without chaos. The sun does not need to act, it only needs to exist. Existence in this context is enough to bend paths, sort outcomes, and write the quiet law that motion plus mass equals stories worth telling. So when we say 3IATLAS is not aiming for Mars, we are honoring the real lead. The sun set the stage and set the curve. Everything else is a cameo. In the next chapter, we will trace how the appointment with a particular orbital lane happens, turning geometry into a rendezvous that looks fated from our vantage point, even though it is simply the timetable of moving worlds. Chapter 4, The Geometry Trick. Why does the path skim Mars rather than Earth or Venus? Timing and angles. Picture the planets as runners on different lanes, each with its own speed. The comet cuts across the track at a slant. Where the slanted shortcut meets a lane depends on when the runner gets there. This pass happens to line up with Mars's lane, not because Mars lassoed the comet, but because the appointment was booked by orbital geometry months in advance. Start by imagining the solar system as a gigantic clock face. The sun sits at the center, and each planet is a hand that sweeps around at its own pace. Earth is the brisk minute hand, Mars is the slower hour hand, and Venus hums along in the fast inner loop. Our interstellar guest is not a hand at all. It is a straight ruler someone tosses across the clock at an angle. That ruler crosses the circle of each hand at a different mark on the dial. If the hour hand is passing the 3, when the ruler arrives, they will appear to meet there. If it is passing the 7, the meeting moves. No drama, just choreography. This choreography has a few key beats. First is the plane of travel. Most planets share nearly the same flat sheet of space, which we call the main plane of the system. The comet's plane is titled relative to that sheet, like a slice of paper slipping through the pages of a book. The line where those two imaginary sheets cut each other is special. It is the crossing line, the track where the comet is guaranteed to pass through the planetary playground. Where that line happens to lie in space decides which orbits it can intersect and at what longitudes. Next is the location of closest approach to the Sun, the low point of the curve that the comet follows through the central gravity bowl. Place that low point in your mind, then draw the comet's slanted plane through it. Now spin the planets along their circular lanes. The ones that swing near that slanted line near the same time will seem favored, not because they tug more, but because the lanes overlap at the right moment. A meeting is simply where a path and a schedule shake hands. Mars wins this round because its long loop and the comet's slanted slice overlap at a time when Mars is actually there. Earth and Venus may have lanes that the slice also cuts, but if they are late or early by even a modest fraction of their year, the meeting evaporates. That is the difference between stepping onto a moving escalator and stepping into the gap where the stairs would have been a heartbeat before. Space is kind, but it is not going to move the escalator back for you. There is also the matter of speed on the lanes. Venus whips around quickly, Earth moves at a comfortable cruise, and Mars takes its time. The comet arrives with a decisive pace, and that pace decides how long it spends near any given distance from the Sun. If the visitor blitzes through the region where Earth might meet it, the window is short. If the timing lines up a little later when Mars is cruising by the crossing line, the window is wide enough for a photogenic pass. Think of it as train platforms. A fast express roars past platform 1 in a blur, but lingers for a handful of breaths near platform 2 because of the curve of the track and the schedule posted weeks ago. Angles on angles give us the rest of the story. The path where the comet pierces the main plane has 2 gateposts, one where it dives downward across the sheet and one where it climbs upward. Those gateposts drift only slowly under the influence of distant tugs, which means we can forecast where the slice will cut the lanes long before the comet becomes bright. Once we know those gateposts and the time of the Sun's swing, we can work out a rough geometry of who will be nearby. It is like knowing 2 highway exits and a general time of arrival. You can already guess which diners will be open when you pass. From Earth's point of view, perspective adds a fun twist. Project the 3-dimensional dance onto our sky, and the comet's path can appear to aim toward one planet. Even when in space, it never gets particularly close to that body's actual position. Lines on a map can mislead if you forget the depth. This is why star charts show both where things appear and, in small notes and tables, how far they truly are. A near miss on paper can be a very wide berth in space, and vice versa. The sky loves an optical illusion. It is the original street magician. Parallax, the change in apparent position caused by observing from different spots, can spice this illusion further. Observers on Earth, on spacecraft around Earth, and on platforms near Mars each see a slightly different line painted across the stars. The comet's path is the same. The lookout towers are not. Keep switching towers, and you can make the arc seem to lean or straighten, which is useful for measuring distance, but notorious for confusing casual viewers. The universe is not being coy, it is just giving you stereo vision. None of this requires any special pleading about attraction to a specific planet. The lanes are fixed by the laws of motion. The slice is fixed by the comet's incoming direction and energy, and the meeting point is fixed by calendars that planets keep with fanatical discipline. Mars happens to punch the time card at the crossing on the right day. Earth and Venus punch their cards elsewhere. If this feels suspiciously like fate, remember that fate in space is just math wearing a cape. A final image to lock the idea in place. Take a paper globe and draw 3 rings around the equator for the orbits of Venus, Earth, and Mars. Now spear the globe with a skewer at a jaunty tilt to mark the comet's plane. Rotate the rings until one of them lines up under the skewer, where it emerges. That is the near pass. If you turn the rings a little, the near pass moves to another ring. You did not change the skewer, you changed the timing of who arrives under it. That is orbital geometry doing its quiet, inevitable work. In the next chapter, we will step off the racing oval and whisper about the large, distant watcher, whose subtle nudge can change where that skewer pokes through the globe. long before anyone notices. The headline reads, Small Pushes, Big Stage Effects. Chapter 5. The Stage Hands You Do Not See. Jupiter's distant pull shapes many inbound paths, long before comets get famous near the Sun. Even for an interstellar visitor, a brush with a giant planet's gravity can nudge a trajectory. It is like a backstage crew member who bumps the scenery and the whole set slides 2 centimeters. Tiny change, big consequence downstage. Begin with a truth that loves to hide in plain sight. The giant of our system is not just a planet, it is a roaming region of influence. Picture space as a grand theater. The Sun owns the stage, sure, but Jupiter controls the fly system, the trapdoors, and the cables that raise the scenery. You may not see the rigging from your seat, yet every entrance and exit pays respect to it. When a traveler sweeps in from deep space, if the path threads anywhere near that moving zone of influence, the visitor will feel a tug, not a shove, just a quiet suggestion that becomes a storyline later. This zone has a practical boundary, a bubble where Jupiter's pull outruns the whispers of the Sun for nearby objects. Think of it as the planet's personal rehearsal room carried along in its wide path. Most guests never walk straight through that room, but they can loiter in the hallway, and hallways matter. Even a pass a long way off can tilt the guest's route by a sliver. Over the vast distances between the outer and inner system, a sliver grows into a shift you can point to on a chart and say, there, that is why the comet arrived half a week earlier and a few million kilometers to the left. Why are small nudges so effective? Because deep space is the land of long leverage. A small change in direction far away acts like a tiny turn of a ship's wheel far out at sea. Give it hours and the shoreline it meets is different. Give it months and you are waving to the wrong lighthouse entirely. Jupiter is the sailor who flicks that wheel while pretending to admire the sunset. The flick is not malicious. It is just gravity, doing what gravity does when large masses glide past smaller ones. There is a second trick up the giant sleeve. Moving targets add or subtract speed without touching. Sailors call it stealing wind. Navigators call it a gravity assist. Our visitor does not need a meet and greet to feel the effect. Passing Jupiter from behind can lend the traveler a little extra forward push in the Sun's frame of reference. Skimming in front can take a little away. The change may be modest, but timing is sensitive. Arrive at the inner system with a slightly different pace, and you cross different longitudes at different hours, which is how a pass that could have seemed near Earth becomes a pass that favors Mars, or vice versa. Space navigation, now with jazz. The geometry of these encounters is drawn on an imaginary page called the approach plane, the sheet you would get if you froze the moment of closest swing and flattened the incoming and outgoing paths onto a map. On that map, a point exists for every possible approach, and certain small regions act like doorways. Slip through one doorway, and your exit path points inward a little more. Miss it, and you sail outward a little wider. People who throw spacecraft at planets spend late nights studying those doorways. Comets, of course, are not reading textbooks. They stumble through or around them courtesy of chance. The result is a choose-your-own adventure, written by Mass and Motion. Chaos, the friendly kind, makes an appearance here too. Not chaos as in nonsense, but chaos as in delicate dependence on details. Shift the incoming line by a body length, and the future swing can change from noticeable to dramatic. Flip the spin of the nucleus, and tiny jets may aim a whisper of gas during the pass, and that whisper, times long travel, becomes a new appointment date closer to the Sun. We will leave those jets to another chapter. Today's point is that Jupiter sets the stage on which small changes actually matter. The giant planet is the amplifier. Quiet strums become audible riffs because the speaker is turned up. Think about history for a moment. Early in the life of our system, the giant did not merely nudge, it sorted. The great planet scattered leftovers, parking some in the distant cold and ejecting others into interstellar night. That ancient rearrangement still echoes. The lanes that modern visitors use are shaped by this old traffic pattern. Roads remember the bulldozers that cut them, and our cosmic roads were definitely built with a heavy machine that answered to Jupiter's name. When a stranger from another star drifts through, it encounters an architecture already skewed by the Titan's long reach. For observers, Jupiter's fingerprints show up in patterns. A family of comets might share similar tilts or similar swing distances because the giant planet has been whispering the same suggestion to all of them for centuries. Interstellar travelers are rarer, yet the logic holds. A skim near the giant can rearrange the angle at which the stranger approaches the inner system and the hour at which it arrives. You do not need the planet to kidnap the traveler for the traveler to show up with a story that says, "I passed a bouncer in a tuxedo and he asked me to try the other door." A quick human metaphor to keep us smiling. Jupiter is the universe's stern head usher. It does not decide what the play is about, but it does decide where you sit if you stroll in late. Front row left, second balcony right, or standing room near Mars. No arguments, please. Your ticket says gravity, not freedom from seating assignments. What should we look for as the interstellar guest arcs inward? Subtle coarse refinements that show a memory of a distant brush, brightness rhythms that suggest a changed spin from an old nudge, a timetable that lines up just so with Mars, rather than other worlds because an hour was borrowed or returned far away. None of these clues stand alone, but together they sketch the shadow of a giant hand adjusting the light. In short, the stage hands you do not see are busy. One of them wears a striped storm coat and wields a gravity wrench large enough to tune the orchestra from the lobby. Our visitor's path carries faint fingerprints from that wrench. In the next chapter, we will trade giant planets for the subtle weather around a star, where light itself gives a push and charged winds comb tails into banners. Space may be quiet, but the breeze is real. Chapter 6. Solar wind and light pressure. Sunlight is not just light, it carries momentum. Photons push, the pressure is small, but on a fluffy, outgassing comet, small is not trivial. The solar wind adds a charged breeze that rips dust and gas into long tails. None of this targets Mars, but it shapes the comet's speed and orientation, which changes when and where it crosses the red planet's lane. Space weather is basically the universe's version of bad hair days. Let us start with the quiet shove from light itself. Imagine standing in a drizzle, so fine you barely feel it, yet over hours it nudges a door until it swings open. Sunlight does that to tiny grains that peel off a comet's surface. Each photon is a tiny tap. One tap is nothing. A river of taps, day and night, becomes a real push. For a boulder, that push is a joke. For a fleck of soot or a powdery chip of ice, it is a lifestyle choice. The result is size sorting in motion. Smaller bits get bullied more than larger ones, drifting faster away from the direction of the sun. The comet sheds a cloud that stretches, thins, and streams, not because the sun is bossy, but because the physics of many tiny taps rewards the light and the fragile. Now mix in the solar wind, which is not wind in the breezy picnic sense, but a continual outflow of charged particles and magnetic fields from the sun. Picture a river of invisible marbles laced with elastic threads, racing outward in all directions. When those marbles slam into atoms that escaped from the comet's surface, they strip electrons and herd the newly charged particles along the elastic threads. The flow does not so much blow as it organizes. It takes a chaotic fog and lines it up as if the universe said, "Please form a queue." That queue can kink and twist when the magnetic threads wiggle, which they do, often, because the sun's outer layers simmer like a pot that never quite settles. Neither the photon push nor the charged breeze is constant. The light pressure changes gently with distance from the sun, like stepping closer to a campfire and feeling a stronger glow on your face. The solar wind, on the other hand, is moody. It speeds up when dark holes open in the sun's atmosphere. It slows when denser belts roll through, and sometimes it throws a tantrum in the form of a massive ejection. that sends a shock wave humming through space. When one of those shock fronts meets the cloud from a comet, the whole structure can flutter, brighten, or pivot in hours. Think salon day meets leaf blower? All of this fuss matters for motion, not just for looks. When the comet vents gas, the smallest grains lift first and feel the photon push most. That means the center of mass of the nearby cloud shifts a little, which changes how sunlight warms the surface underneath on the next spin. A patch that was shaded becomes bright. A bright patch moves into dusk. The pattern of heating evolves. Over many rotations, that evolution steers which areas vent tomorrow. The path through space is still ruled by the sun's gravity, but these gentle, persistent pushes and rearrangements act like fingertip corrections on a violin string, just enough to tune the note. Timing shifts by minutes here, by hours there, and a predicted crossing of a planet's lane can move slightly forward or back on the calendar. Space has no traffic lights, but it certainly has headwinds and tailwinds. There is another layer, orientation. A comet is not a rigid dart. It is a lumpy spinner. As it rotates, sunlight strikes slopes at different angles, setting up warm and cool zones that migrate across the surface. Warm zones tend to feed more vapor into space, creating local drifts of dust that light can push. The pattern of these drifts can apply gentle torques, the kind that very slowly adjust the spin period or the tilt of the rotation axis. Change the spin, and you change which regions get the morning sun next week, which changes the drifts again. The whole system is a feedback loop that trades whispers with the star. It is not dramatic enough to throw the comet across the solar system, but it is more than decor. Over millions of kilometers, whispers move maps. Because the solar wind carries magnetic fields, it also builds a protective bubble around the outflowing gas from a comet, a kind of mini magnetosphere that grows and shrinks with the wind's mood. At the boundary of this bubble, charged particles from the sun and fresh ions from the comet negotiate who goes where. Sometimes the boundary is smooth, sometimes it wrinkles into waves. Those wrinkles can funnel energy deeper into the cloud, making certain regions emit more light or kick off particles in preferred directions. Observers watch these changes to read the space weather forecast, the way sailors read ripples on a bay. From our vantage point, all these pushes translate to measurable shifts in position over time. Careful tracking of the comet against background stars reveals that its course is not perfectly what gravity alone would draw. There are tiny deviations consistent with light pressure and wind coupling. Those deviations tell us about the fluffiness of the dust, the typical grain sizes, even how porous the surface might be. It is like listening to the way a coat flaps to guess whether it is wool or silk. You do not need to pull a thread. The sound gives it away. Importantly, none of this is a homing system that prefers one planet over another. The pushes have no opinion about Mars, Earth, or Venus. They respond to distance from the sun, to the object's own rotation, and to the current mood of the wind. Still, by reshaping the exact schedule and orientation of the visitor, they can change the fine print of a near pass. Arrive a touch earlier, and a runner in one lane will be nearby. Arrive a touch later, and a different runner gets the view. Cosmic photo ops are often decided by the equivalent of a gust. If you want a mental snapshot, imagine a dandelion seed drifting across a warm sidewalk. Sunlight heats the air unevenly. A car whooshes by. A child waves a hand. The seed has no steering wheel, yet it traces a path that looks almost intentional. Our interstellar traveler is that seed, only scaled up to wild proportions and coached by rules that look gentle until you give them time. The finish line is the same general neighborhood, but the exact doorway it brushes is a product of 1,000 almosts. In the next chapter, we will zoom from outside forces to internal plumbing and meet the little thrusters a comet makes for itself, where vents act like nozzles and every puff writes a footnote on the flight plan. Chapter 7, Comet Jets as Thrusters. As the sun warms the nucleus, buried ices vaporize through cracks and vents. Those jets act like microthrusters, giving random nudges that slightly rotate and adjust the path. Imagine a leaky firework rocket whose spray pushes it a little left, then a little right. Over millions of kilometers, a little is a lot. In mission control, those are called non-gravitational forces. In comet world, that is just Tuesday. Picture the nucleus as a lumpy, charcoal dark boulder with pockets of frozen gases sleeping beneath a dusty crust. Dawn creeps across that surface, and the top few fingers of material wake first. Heat trickles downward with the patience of a librarian, and when it reaches a seam or a cavity, the ice inside goes from quiet to restless. Gas seeks escape, and the easiest path is through fractures left by ancient stress. Where the crack widens to daylight, the comet exhales. It is not a gentle sigh. On small scales, it is a geyser, a fountain of vapor that drags dust grains along for the ride and fans into a jet shaped by the surrounding terrain. If you stood nearby, which I do not recommend because you like staying alive, you would hear silence and feel grit whisper past at highway speed. Each jet is a nozzle without hardware. The plume shoots backward, the nucleus creeps forward. The push is tiny compared to the pull of a star, but it does not need to be big to matter. The secret is leverage. A steady puff from one side can add a hair of speed or take a hair away. A puff off center can twist the spin. A train of short bursts that fire in daylight and fade in darkness can create a kind of heartbeat, changing orientation with a rhythm tied to the comet's day. Over many rotations, the heartbeats accumulate into a noticeable tilt change or a measurable drift along the flight path. You will not see the nucleus sprout wings, but the numbers will. You can think of the surface as a patchwork of microclimates. Some regions are sun-facing during local morning and become active for a few hours. Others lurk in shadow and barely stir. Ridges break the light, craters hoard shade, and cliff faces dump debris that briefly covers vents like corks. When the cork pops, the pressure release can surge, and for a short time, the nucleus gets a larger nudge than usual. These outbursts are the jump scares of comet life: sudden brightening, spurts of dust, and a slightly altered spin that the object will live with for the next few weeks. Space horror movie, minus the soundtrack. Beneath the dust, ice can recede unevenly. Think of a slow-burning candle that tunnels from the inside, leaving a fragile roof. When that roof collapses, a new vent opens, and an old vent chokes. The pattern of thrust changes yet again. This is not a polite engine with a manual and numbered valves. It is a kitchen with too many kettles and a habit of moving the stove. A mission planner would cry. A scientist grins, because every twitch reveals something about where the fuel pockets are, how thick the crust is, and which minerals hold the heat like a stubborn memory. The direction of each push depends on local slopes and the way the gas expands into vacuum. A narrow throat makes a tighter plume that points like a flashlight beam. A broad mouth spreads the flow like a garden sprinkler. If the comet spins while the jet is firing, the thrust vector sweeps a cone, and the average push may point somewhere between the start and end positions. That makes prediction an art that mixes maps, light curves, and a dash of intuition. Observers measure the position night after night and watch for tiny offsets from the expected track. Those offsets form a breadcrumb trail, leading back to the invisible engine room. Spin states are a whole subplot. A jet that fires near the equator can speed up or slow down the day length, depending on whether it blows with or against the rotation. A jet near a pole tilts the axis slightly, which alters which regions get morning next week. This reshuffles the activity calendar, which reshuffles the thrust pattern, which changes the spin again. It is a self-editing script, and somehow the actors keep hitting their marks. When the axis tilts enough, a once sleepy crater can enter a season of sunlight and become a new source of push, while a former hotspot slips into months of night and rests. Comets run on seasons the way bears run on naps. Grain size in the plume matters for momentum transfer. Fine powder couples easily to the gas flow and leaves swiftly, boosting the jet's efficiency. pebble-sized fragments are heavier and may arc up and rain back down, mantling vents with fresh debris that muffles future puffs. Sometimes the returning hail slides downhill and exposes a clean patch that launches the next burst even stronger. The landscape is a feedback machine. Activity modifies terrain. Terrain modifies activity. It is like a city where road construction creates traffic, and traffic changes where the next construction happens. Urban planners everywhere feel seen. Not all jets are steady commuters. Some are commuters who discover espresso. When a sealed pocket finally warms to a threshold, pressure breaks through a thin crust, and a plume roars for minutes or hours. During that window, the thrust can be orders of magnitude stronger than the background coughing elsewhere on the surface. The nucleus lurches, minutely but measurably, then returns to its usual fidgeting. Think of it as a hiccup that moves your chair an inch. You did not cross the room, but the table is no longer aligned. Do these homemade thrusters decide which planet gets a close look? Not in the sense of choosing favorites, but yes, in the sense of shifting arrival times and orientations. If the jets add a nudge that makes the comet reach a particular distance slightly earlier, the celestial lanes it intersects will be occupied by a different runner. That is how a schedule slides without a grand conspiracy. The way a single red light on your commute swaps which song is playing when you pull into the driveway. The destination is the same neighborhood. The exact neighbor waving from the porch changes. If you want an image to keep, imagine a stone skipping across a lake while tiny fish flick its underside at random moments. The stone's grand arc is set when you throw it, but those tiny flicks add wobble and change where the last skip kisses the water. That is the poetry of comet jets. Small forces, long runways, big narrative payoff. Next up, we will step outside the engine room and talk about perception itself, how vantage and mapping can make a pass feel like a rendezvous, and why our eyes love to turn crossing lines into romances. Chapter 8, Why Toward Mars Feels True. From our point of view, the track lines on a star chart show the comet's arc narrowing toward Mars's orbit. That visual tempts a story about attraction. The real story is overlap, not magnet. Mars's gravity will add a tiny tweak during the pass, but the Sun did the heavy lifting long before the cameo. Mars gets the photo op, the Sun gets the producer credit. Begin with a confession about the human brain. We are world-class at connecting dots, and only bronze medalists at resisting a juicy narrative. When two lines on a map lean toward each other, our instincts yell, rendezvous. Railroad tracks seem to meet at the horizon, even though the rails keep their distance. Airline routes on a flat poster look like strange curves, but that is the map fibbing about a round world. Star charts pull the same trick. You see a graceful arc bending across constellations and brushing the symbol of Mars, and your brain whispers, it is headed there. Your brain is not lying, it is storytelling, which is adorable and occasionally misleading. Words matter too. We say an object is heading for a planet when we mean it will pass near the planet's path, as seen from where we stand. Near does heavy lifting in conversation. Near an angle is not the same as near in space. Two birds can cross the same line of sight from your window and still be far apart in altitude. The comet's apparent path and Mars's plotted orbit can overlap on paper, while their actual separation remains vast. This is why astronomers keep two calendars in their heads, one for how things look on the sky, and one for where they are in three-dimensional space. Drama lives in the first calendar. Reality signs the checks in the second. There is also a camera angle issue. Observing from Earth is like filming a parade from a fixed balcony. Floats seem to line up, dancers seem to pass behind each other, and the band looks dangerously close to the confetti cannon, but depth is hard to judge. Shift to a different balcony, and the same moments rearrange. Spacecraft around Mars will get their own balcony view. Their footage may show the comet and the planet farther apart than our earthbound eyes expected, or closer, depending on the geometry. Neither view is wrong. Each is a slice of a larger truth. The universe offers no single master shot. It is all multi-camera. Language adds another coat of paint. Phrases like closing in on and bearing down on are catnip for headlines, but sneaky with physics. The comet is not hunting a world. It is tracing a freefall shaped by the central star. The timing that makes the pass look Mars-flavored is not courtship, it is choreography. Still, if you are a mission planner who loves headlines, you do not argue. You smile, prepare instruments, and let the moment sell itself. A great picture taken from Mars's neighborhood is worth 1,000 caveats about projection effects. Then there is the tail, the showy scarf that always seems to point away from the sun. If Mars happens to be somewhere downwind from Earth's vantage, the tail can look like an arrow aimed at the planet. That is pure optics. The tail is a windsock for solar weather, not a pointer at destinations. Yet our eyes cannot help reading arrows as intent. It is the same magic that makes a crooked branch look like a finger telling you where to walk on a trail. Spoiler, the branch has zero opinions about your hike. Charts sharpen illusions with symbols. Planetary orbits are drawn in neat, crisp loops. The comet's track is a clean spline curving across the grid. Where lines cross, your attention snaps to the intersection like a magnet. But those lines have thickness in real space. The planet's loop is a three-dimensional ring. The comet's path is a tilted ribbon slicing through the ring's neighborhood. Their intersection on paper is a mathematical shadow, not a promise of a handshake. If you could float above the model, you would see layers, not collisions. Our curiosity also loves heroes and supporting characters. Mars wears a dramatic color and hosts robots with cameras, so it steals scenes. When a traveler from afar passes vaguely in its vicinity, the story writes itself. Mars, center stage, guest star incoming. The actual center of influence remains the star at the middle, quietly bending the whole act. But quiet does not trend. The sun is the reliable bass player. Mars is the flashy lead guitar. Both are essential. Only one gets the solo. You may have noticed that predictions of closest approach distance and time evolve as more observations roll in. That is not because the comet changes its mind every week. It is because more data shrinks uncertainty in our knowledge of its position and motion. Early on, the corridor of possible futures is wide. As nights of tracking stack up, the corridor narrows, and the projected pass stops sliding around the screen. If the corridor happens to narrow across Mars's orbital lane, we feel vindicated. See, it was always going there. Careful, what you are witnessing is the math focusing, not the comet swerving. A quick exercise to decouple appearance from reality. Hold a coin at arm's length and line it up so it covers a distant streetlight. The coin now touches the lamp in your field of view. Step sideways and the illusion breaks. Space does that with comets and planets, only with less stepping and more orbits. Two things can share a sightline today and be nowhere near each other in distance. The sky is a champion at forced perspective. So why keep the phrase toward Mars at all? Because it is a useful shorthand for where to look, for which instruments to wake up, and for which orbiters might score bonus science. It is navigation speak, not destiny. If you catch yourself imagining Mars reeling the traveler in with a lasso, smile and adjust the picture. The lasso is a timeline, the knot is a coincidence, and the hand holding it belongs to geometry, not to a planet with opinions. Here is the payoff. Understanding why the phrase feels true makes the moment sweeter, not smaller. You are in on the trick. You can enjoy the spectacle and still appreciate the clockwork that set it up. And when the images arrive from the red world's neighborhood, you can grin at the headline and whisper to yourself, "Nice cameo." In the next chapter, we leave appearances behind and talk about those hidden neighborhoods in space where repeated tugs stack up, the resonance cul-de-sacs that can shape streams of debris even for a one-time visitor. Chapter 9. Resonances and near misses. Space has lanes where repeated tugs accumulate. These are orbital resonances, and they can sculpt asteroid belts and comet trails. An interstellar comet is a one-pass traveler, but it can still glide through resonance neighborhoods, picking up subtle kicks. Think of it like tapping a swing only once, yet still changing the arc a little. One nudge, noticeable difference. Start with a household image. Put a line of metronomes on a table and set them walking at nearly the same tempo. At first, they clatter out of step. Give them time, and the tiny vibrations of the shared tabletop bring them into sync. Nothing magical happened. The table carried small pushes that happened at just the right rhythm. In space, the tabletop is the shared gravitational field, and the steady beat is the repeating orbital motion of planets. When an object loops the sun again and again, those tugs hit on the same beats, and the effect piles up like interest in a very patient bank. That piling up is resonance. But what about a guest that passes only once? No savings account, no compound interest. Even so, the guest can cruise through districts where the timing of pushes is organized by the long-term dance of planets and debris. Those districts are full of standing patterns, like waves in a harbor that keep sloshing in set places, even when a single boat crosses only once. A quick surf across a standing wave still changes your bow angle. The pass does not turn a stranger into a resident, but the path can leave with a slightly different lean than it arrived, especially if the crossing happens when a planet is at just the phase that lines up a few nudges in a row. You can see resonance's fingerprints in the asteroid belt. There are gaps where you would expect many rocks, and piles where you would expect few. The gaps trace locations where a small body would circle in a rhythm that repeats against a giant planet's year, taking a tug at similar points each time. The constant drumbeat shakes those orbits loose over ages, sending rocks to new addresses. The piles trace rhythms that protect rather than disrupt. Neighborhoods where the repeating beat smooths out slight missteps and keeps the residents in step like a good ballroom coach. That is resonance as sculptor. Carve here, polish there, repeat for a few 100 million years. Our interstellar visitor does not linger to be carved, but it can drive through the workshop while the chisels are still humming. When it does, it encounters not just raw gravity, but gravity arranged by timing. Imagine a city grid where most lights are synchronized. If you hit the first green at the right moment, you surf a whole boulevard of greens, even if you will never drive that way again. If you arrive half a block off, you meet a sequence of reds that slows you and shifts where you make the next turn. The grid did not care about you personally. The timing was already set. Resonance districts in space are that grid. There are also deeper, slower patterns called secular resonances, the long tide that very gradually twists orbital shapes and tilts. They work not by quick shoves each lap, but by biasing the average direction in which an orbit's long axis or its tilt slowly turns. Most of the time, you need many laps for this slow tide to matter. A one-pass traveler is not around to feel the whole tide, but it can still cross the shoreline where the tide is strongest and get a small, clean push, aligned with that preferred twist. It is a brief handshake with a very patient process. Near misses bring their own kind of timing. Every flyby has a plane of closest approach, and within that plane, tiny windows called keyholes, where a small difference in miss distance would lead to a very different later path. For repeat visitors, keyholes can separate a safe tour from a future collision after one or more loops. For a hyperbolic guest, there is no later loop in this neighborhood, but the idea still illustrates how structure fills space. Even within the broad zone of near passage, there are threads and filaments of different outcomes. Slip a little to one side of a filament, and you leave a touch faster. Slip the other way, and you leave a touch slower. Think spiderwebs, not empty rooms. Another way to feel this structure is to picture invisible lanes that guide low-energy motion around planets, shaped by the combined pull of the planet and the sun. Space navigators sometimes ride these lanes with spacecraft to save fuel, letting gravity do the work while missions hop from one friendly corridor to the next. A comet on a fast pass is not parking in those lanes, but it can cut across them, Even a quick slice through a corridor can bend a path a hair more than an otherwise identical slice, a few thousand kilometers away. The difference is not cinema big, but prediction grade important. Resonances can also influence what the comet leaves behind, not just where the nucleus goes. Dust grains shed on the way in or near closest approach do not all follow the parent exactly. The smallest float away under light pressure. Medium grains stay near and travel on their own slightly offset orbits. If those grains happen to be released where a resonant pattern sweeps through, the pattern will tend to shepherd some sizes into streamers and disperse others. Months later, observers might see a faint ribbon tracing the route, a delicate afterimage drawn by timing rather than by a single explosive event. It is the celestial version of a contrail aligning with a jet stream. Because resonance is about rhythm, it is also about phase, which is a fancy way of saying where in the beat you stepped onto the dance floor. Two passes through the same district at different phases can feel entirely different. One arrives during a harmony of pushes and leaves, humming a new tune. Another arrives during a cancellation of pushes and slides through with barely a note. For science, that means we must keep both geometry and schedule on the chalkboard. Where and when share custody of outcomes. Let us anchor this in a final picture. Imagine a skate park, frozen in time. Bowls and ramps curve in graceful shapes. Now roll a single marble across it once. You will never see the long game of a skater practicing for years, but the marble still feels the molded lines. It dips a little where the bowl is shallow, crests a little where a lip rises, and exits at an angle set by the park's design. Resonances are the molded lines of the solar system. Our comet is the marble. One ride, real influence. Next, we will leave patterns and timing and walk the practical aisles. How we measure the changing light from the traveler to read the ingredients inside, and how those colors and lines turn into stories about distant kitchens where icy recipes were first mixed. Chapter 10. Why not Earth? Swap Mars and Earth in your mental model. If our planet had been at a certain part of its path a few weeks earlier or later, the apparent aim could have been toward us. The cosmos did not prefer Mars. The calendar did. Space is not personal. It is punctual. Start with the simplest clock you own, the one your body keeps when you wake a few minutes before the alarm. Planets keep a version of that clock. Earth finishes a lap around the sun in 1 year. Mars takes longer. That means the two worlds drift in and out of alignment like dancers who learn the same routine at different speeds. Every so often, they share the same neighborhood of space at the same time, and sometimes they miss each other by a small eternity measured in weeks. Our interstellar visitor is cutting across the ballroom once. If Earth is mid-twirl across the floor when the crosscut happens, we get the close view. If we are still tying our shoes at the edge of the floor, the spotlight falls on someone else. Picture a railroad junction where a fast express line crosses a ring that carries local trains. The express is the comet. The ring is the family of planetary orbits. The crossing point is fixed in space by the comet's unique approach, but the trains arrive there on their own schedules. If Earth were due at the junction on Thursday afternoon, we might wave at the express through the window. Instead, Mars is pulling in Tuesday morning. Earth does not get snubbed. Earth gets rescheduled. Space is basically one giant timetable with nobody at the help desk and still, mysteriously, no delays. Timing is not the only filter. Orientation matters too. Earth's path is slightly tilted compared with the visitor's slicing plane, and the two do not always intersect at the elevation where Earth happens to be. Think of two highways that cross at different overpasses. On a paper map they meet. In real life, one is sailing overhead while the other sneaks through a tunnel. If Earth is on the upper deck when the comet barrels along the lower deck, the view is good, the distance is large, and no one merges. The difference between breathtakingly close and comfortably far can be a few million kilometers, which sounds large until you remember that space measures distances the way oceans measure moods broadly. Now add Earth's own quirks. We live under an atmosphere, that loves to turn good sky plans into weather reports. Even when the geometry is decent, clouds, daylight, and the moon's glare can sap drama from a pass. Mars, on the other hand, is an entire world of cameras with different schedules and different local skies. If robot eyes around Mars happen to be awake with the sun behind their shoulders, they score images that our ground telescopes might never match. Earth can look like it was left off the guest list, when really it was just stuck behind the world's thickest velvet rope, our air. There is also the safety angle, which is less thrilling than a near miss but more comforting. People hear aimed at and think headed for. Those are not the same. Aimed at is a headline about direction within a flat drawing. Headed for is a statement about converging paths in three-dimensional space. The first can be dramatic with very small risk. The second is reserved for rare, genuinely close approaches. It is the difference between seeing a bird's shadow sweep across your lawn and a bird actually knocking on your window with tiny bird knuckles. The former is common, the latter makes epic videos. Let us talk seasonality. Earth's nights are longer and darker in certain months. If a comet's best show happens during short nights with the target low on the horizon, our view is brief and murky, even if the geometry says we are not far away. Mars does not share our weather or our calendar. It might enjoy a longer window just because its local day and season line up with the visitor's best angle. In that sense, why not Earth can be answered with because our planet had other plans. It is not rejection, it is scheduling conflict. Another subtle piece is our motion around the sun combined with the comet's motion past the sun. When two moving objects pass, their relative speed decides how long we get to gawk. A small change in timing can shrink a week of good viewing into 2 hurried nights. Mars's slower beat around the sun sometimes grants a longer linger near the crossing line, which makes a pass feel richer, even if the raw distance is similar. Imagine 2 friends waving from separate trains. If both are traveling in nearly the same direction, the wave lasts. If they zip past in opposite directions, the wave is a blink and a shrug. We should also give credit to perspective's favorite trickster move, the difference between angular closeness and physical proximity. Earth could see the comet glide very near Mars in the sky, almost brushing the planet's glow from our line of sight, while the real separation remains wide. Viewers might tease, "It missed us by a hair," when the hair in question is the size of several worlds laid end to end. Space loves generous margins. Engineers love them more. If all this sounds like Earth keeps missing the party, take heart. Our vantage is often the best for tracking a newcomer over many weeks. We have a whole planet's worth of telescopes that relay observations across longitudes, like a relay team that never sleeps, even when the visitor is not ours. We are the newsroom writing the first draft of its biography. Plenty of science happens outside the glamorous close pass. The universe may hand Mars the selfie stick this time, but Earth publishes the album. Here is the useful takeaway. Replace the idea of favoritism with the idea of phasing. Swap romance for routine. The comet crosses the lanes it must cross when it must cross them. Planets arrive where they must arrive when they must arrive. This time, the overlap favors Mars. Next time, it could be our turn, or Venus's turn, or nobody's, with the best action unfolding far from any world. Space is fair in a very specific way. It treats every object like a slave to the calendar. In the next chapter, we will pivot from who gets the close pass to what a close pass actually does for the so-called host planet. We will weigh Mars's modest pull during the flyby and explain why a cameo does not become a capture, even when the camera angle screams romance. Chapter 11. Mars's actual pull. Mars is smaller than Earth and far smaller than Jupiter. Its sphere of influence is modest. During the flyby, Mars will tug, but the comet will not spiral into orbit. Capture would require a huge energy loss, like slamming on the brakes while rolling downhill on ice. With no giant air drag and no escort moon to steal momentum, capture is a cinematic fantasy. Fun to picture, not on the menu. Think of gravity here as a set of overlapping bubbles, carried by each body as it orbits the Sun. The Sun's bubble is a cathedral that fills the stage. Inside it, every planet tows a much smaller bubble where its guidance matters most. Mars's bubble is more like a cozy studio apartment compared with Jupiter's sprawling mansion. When an interstellar comet rushes through, it spends most of its time obeying the cathedral's architecture. Only for a brief interval does it feel the studio's decor. A nudge, yes. A lease agreement, no. Capture, in plain terms, means the visitor must leave with less go than it arrived, enough less that the planet can keep it. That means throwing away a mountain of motion. Space has only a few ways to throw away motion quickly. One is drag in thick air. Another is a carefully staged handoff between multiple bodies so that momentum shuffles around like chips in a card game. Mars is not built for either. Its atmosphere is thin, great for rover selfies, terrible for breaking a bullet made of ice and rock streaking in from deep space. To slow the comet with air, the path would have to dip so low that heating would turn the encounter from science to fireworks. Error capture is a cool word. It is not a realistic outcome for a hyper-fast stranger at Mars. What about the handoff trick, the gravity assist hopscotch that spacecraft use so well? That game works when the traveler threads a path that lets a planet's motion donate or siphon a bit of speed, and then another planet follows up, and so on. The key word is bit. You can re-aim dramatically without changing the overall budget by much, to go from free fall past the Sun to a gentle loop around Mars. Demands more than a bit. You would need an improbable chain of events. A very low miss distance, a skim near a helpful moon, perhaps a second encounter after a loop in the neighborhood, all timed perfectly. Mars's tiny moons are not helpful bouncers here. Phobos and Deimos are closer to mountain-sized than moon-sized. They cannot steal meaningful momentum from a racing comet. They can barely boss around pebbles. Consider tides, the silent accountants of close encounters. Big bodies can raise tides on each other, converting motion into internal heat. That is one pathway to losing energy without air. But Mars is not massive enough to tug a sturdy comet into a warm, energy-bleeding embrace during a fast flyby. The time together is too short, the forces too modest, the visitor too rigid for any serious needing. If tidal capture were a dance, this would be the briefest of shoulder taps at a crowded party. Distance matters as much as muscle. The likely pass happens well outside the region where Mars's gravity absolutely dominates. Even while the comet is in the Martian neighborhood, the Sun still plays hall monitor, whispering instructions that outweigh the planet's commands. The result is a path that bends a tiny bit toward Mars, then straightens back toward the grand itinerary set by the star. Imagine tossing a paper airplane across a gym while someone waves a fan from the bleachers. The airplane quivers, drifts a hair, then keeps gliding toward the opposite wall. The fan did something. It did not suddenly own the plane. There is also timing inside timing. The comet moves quickly relative to Mars. A brief interaction limits how much the planet can alter speed and direction. Think of a handshake while jogging past each other. You can redirect a shoulder. You cannot spin someone into a waltz. A longer, slower dance allows deeper influence. That is why giant planets with large bubbles and stronger pulls can remix orbits in profound ways. Mars specializes in cameos, not rewrites. Gravitational focusing, the way a planet's pull slightly increases the chance that a passerby comes closer, plays a role, but it is not a lasso. It draws the path inward by a fraction, changes the exit angle by a smidge, and calls it a day. For scientists, those smidges are precious. They carry information about the comet's mass and the exact geometry of the pass. For storytellers, smidges lack fireworks. The universe is okay with that. Not every scene needs pyrotechnics. Some scenes need quiet precision. Could debris shed by the comet interact with Mars in more tangible ways than the nucleus itself? Perhaps a few dust grains might wander into the upper atmosphere long after the nucleus has moved on, creating faint streaks too subtle for the human eye. That is a side effect, not a capture. The main act remains a flyby, a polite bow, not a proposal. A quick reality check on the rover movie you might be scripting in your head. A grand arc across a pink sky. Then the icy core hooks into orbit and becomes a new Martian moon. Lovely visual. The physics, however, sends notes. To pull that off, the comet would need to arrive with exquisitely tuned speed and angle, scrape deep enough through the air to dump energy without tearing itself apart, and likely share momentum with a hefty companion that Mars does not have. You would be asking a desert breeze to stop a freight train without breaking a single window. The breeze smiles and keeps being a breeze. So what will Mars actually do during the pass? It will tug just enough to make the comet's post-encounter heading whisper a different number than the pre-encounter heading. It will add the faintest tilt to the tale the object tells as it leaves. For observers, that is gold. Tiny deflections are truth serum. They let us refine mass estimates, validate the predicted path, and cross-check the small pushes from sunlight and vents without rehashing old ground. For Mars itself, the event is a front-row seat, a postcard moment rather than a permanent relationship. And that is the charm. Not every cosmic meeting must end in a merger. Some are meaningful because they are brief and precise. Mars gets the cameo. The comet keeps its freedom. In the next chapter, we will use that freedom to our advantage, reading the light that gushes from the growing halo to decode ingredients and temperatures, the way a chef can smell a simmering pot and list the spices without lifting the lid. Chapter 12, What We Can Measure. As the comet nears the sun, its coma brightens and its tail grows. Telescopes will split the light to read fingerprints of molecules, water vapor, carbon monoxide, carbon dioxide, maybe exotic organics that cooked around a different star. Each line in that spectrum is a clue to the chemistry of a distant nursery. Photosynthesis is plants' way of saying we invented solar panels first. Comet spectra are the universe's way of saying here is the original ingredient list. Let us start with the trick of turning light into labels. A spectrograph is basically a fancy prism with trust issues. It spreads the comet's glow into a rainbow so thin you could floss with it, revealing bright spikes and cutouts at precise colors. Those spikes and notches are like barcodes for atoms and molecules. Water vapor leaves one set, carbon monoxide and carbon dioxide leave others, while long carbon-rich chains leave a softer glow that whispers I was built slowly in the cold. When astronomers talk about reading a comet's spectrum, they mean scanning that barcode to see which bottles are on the cosmic shelf. Different parts of the rainbow tell different stories. In visible light, we see emissions from fragment molecules that have been photobombed by sunlight and broken apart. That glow can even shift the comet's color slightly, making some comet look a bit green or a bit blue, depending on which fragments are partying hardest. In the infrared, which is the warm side of the rainbow, we watch heat radiating off dust grains, and we taste gases that vibrate and twist in ways our instruments can hear. Move to the ultraviolet, and you catch the fingerprints of very energetic sunlight, where atoms like oxygen shout their presence with a slim, sharp line that practically begs for a close-up. Radio and millimeter waves add yet another layer, letting big arrays of dishes eavesdrop on cold molecules tumbling end over end. One comet, many voices. The trick is knowing which microphone to hand to which singer. Brightness alone, tracked night after night, is its own gold mine. Photometry, measuring how the glow rises and falls, tells us how quickly the coma swells, how the dust production rate changes with sunshine, and whether the nucleus is spinning with a predictable beat. If the light repeats with a steady rhythm, you are seeing day and night pass across uneven terrain. If it hiccups and surges, you may be witnessing vents opening, crust collapsing, or a fresh patch of ice finally catching dawn. It is weather, but in vacuum, and your forecast app is a notebook full of numbers. Polarization adds a detective's lens to the scene. When sunlight scatters off tiny, irregular dust grains, it becomes slightly polarized, which is a wonky way of saying the light waves wiggle more in one direction than another. Measure that wiggle, and you can estimate grain sizes, shapes, and how fluffy or compact the dust is. A cloud dominated by airy, snowflake-like clumps polarizes light differently than a cloud full of glassy crumbs. Without touching a single particle, you can tell whether the comet sheds powdered sugar or granola, nutrition facts. But for tails, thermal measurements go deeper still. In the mid-infrared, the glow from warm dust peaks like a campfire seen through night vision. The shape of that glow hints at how big the grains are and how efficiently they cool. A grain that radiates heat well will look cooler than a grain that traps warmth. From those curves, you infer how porous the dust is and whether it grew slowly like frost on a window or was shattered from bedrock by a quick exhale. The nucleus itself sometimes peeks through in the thermal data when activity is low, letting us estimate its size and how its surface hoards or releases heat across a spin. That property, thermal inertia, speaks to the crust's texture. Whether it is fluffy like ash or hard like old pavement. We can also weigh motion with light. As gas jets stream out, they shift the exact colors of their spectral spikes by a tiny amount because the emitting molecules are moving. Light from molecules racing toward us is nudged to slightly bluer shades. Light from molecules drifting away is nudged redder. Measure those nudges carefully, and you get the speed of the outflow, sometimes even a hint of direction if one side of the coma is racing and the other is strolling. But I presume there's a radar gun made of rainbows. No traffic tickets, just physics. Chemistry is where the plot thickens. Ratios of water vapor to carbon monoxide to carbon dioxide sketch the freezer the comet grew up in. A nursery that stayed very cold tends to lock in more carbon monoxide. A slightly warmer pantry favors water-rich ices, trace organics, alcohols, aldehydes, and complex carbon chains. Tell us about slow reactions on dust surfaces in the dark between stars. Even the flavor of water can carry a signature, with heavier variants betraying the temperature and density of the cloud where the ice first formed. We do not write formulas here, but the gist is simple. Different kitchens leave different spices on the cutting board. Imaging in special narrow colors lets us map the physics in motion. Point a telescope through a filter that only passes, say, a popular fragment of water vapor, and the coma morphs into a portrait of where that fragment is strongest. Switch to a filter that isolates carbon-based fragments, and the picture changes again. Layer those maps over time, and you get a flipbook of the coma breathing, rotating, and shearing in the solar wind. You are not just seeing what is present, you are seeing how it travels. Sometimes the comet plays with the sun's breeze and creates a shock, a delicate boundary where the outflow meets the onrushing stream of charged particles. Instruments that sense charged particles and magnetic fields can detect that boundary as a ripple, telling us the strength of the wind on that day and how ferociously the comet is venting. It is space meteorology, using a snowball as a windsock. Hairdo, optional, credibility solid. All of this works together. Spectra identify the ingredients. Brightness curves tell us when the kitchen is busiest. Polarization and thermal data describe the utensils. Velocity shifts reveal which burners are on high. And because our guest formed beneath a different star, any oddities in these measurements are clues to alien seasons and distant recipes. If a line appears stronger than expected, or a ratio looks out of place, we are not confused, we are thrilled. That is the whole point of a visitor with an accent. Next, we will hand the best balcony seats to the robots circling the red world and ask what they, and perhaps the surface cameras, can witness from up close. A playbill of vantage points, instruments, and tricks for catching a snowball mid-soliloquy. Chapter 13. Cameras at Mars. Spacecraft around Mars may get a front-row view. Orbiters can snap images, sniff particles, and watch the tail's interaction with the solar wind from a different angle than Earth can. If the geometry cooperates, we could capture changes hour by hour, like a time-lapse of a snowball steaming under a heat lamp. Mars, for once, is the balcony seat with binoculars. Begin with vantage, because in space, point of view is half the plot. From Earth, we often look broadside at a comet. From Mars, an orbiter can pivot to see the visitor at extreme phase angles, where sunlight grazes dust grains and turns them into tiny mirrors. That forward scattered glow can reveal faint structures that are nearly invisible from home, braided streamers, shells from brief outbursts, and pencil-thin rays tracing active vents. It is the difference between looking at smoke from the side and looking along the beam of a flashlight through fog. Details pop, the stage lights do the heavy lifting. Orbiters carry cameras that can switch personalities, wide field for context, narrow field for close-ups. A well-planned sequence might map the coma's size in a sweeping mosaic, then zoom tight on jet fans to catch their flicker as the nucleus rotates. The cadence matters. Hourly shots can show a vent waking with sunrise over the nucleus and fading as it rolls into night. With diligent timing, a whole comet day can be stitched into a flipbook where each panel tells you which regions exhale hardest and which sit quiet, hoarding cold. Space paparazzi, but with lab notebooks. Now add filters. Imaging through color slices, blue, red, near-infrared, ultraviolet, turns pictures into chemistry maps. One pass might highlight dust, another isolates emissions from fragment molecules. Layer those maps, and you see how gas and dust part ways when the solar wind tugs on the ions. Over Mars, there is a bonus: limb scans. Point the camera just above the planet's edge, and the faintest glows stand out against the black, because the bright disk is safely out of frame. That trick is beloved by comet chasers and sunset fans alike. Edge views make the delicate easy. Mars orbiters also tote spectrometers, which are the barcode readers of the sky. From this balcony, they can track how certain lines wax and wane with geometry that Earth cannot easily match. For example, when the tail sweeps across the line from Mars to the Sun, an orbiter looking sunward may catch absorption, the comet's gas nibbling away a sliver of sunlight. That is a backlit measurement, a rare gift that says how dense the outflow is along a very clean path. Flip the angle, and the same instrument watches emission, where molecules glow on their own. 2 angles, 2 stories, one instrument doing yoga. Then there are the plasma and field sensors. These quiet boxes listen to the charged particle river and the magnetic ripples that ride it. As the comet's outflow plows into that river, boundaries form and shift like weather fronts. From Mars orbit, probes can fly through the fringes and read the breeze, how fast the river flows today, how the comet's cloud slows or diverts it, where shock wrinkles appear, where they fade. If an orbiter happens to pass through a fold in the tail, the data will show a sudden change in particle populations, like walking from warm air into air that smells like rain. Space has weather. These are the thermometers and windsocks. Dust counters, when available, offer the tactile version of this story. Each hit is a data point: size, speed, direction. From those impacts, you can reconstruct how the dust spreads with distance from the nucleus, and how sunlight and electric charging sort the grains by weight and fluffiness. A string of small pings could announce a brush with a fine veil. A rare, larger thump could mark a pebble that took a brave leap and then regretted everything. Space, come for the romance, stay for the bean counting. Coordination turns good observations into great ones. Ground teams on Earth can schedule telescopes to stare at the same moment an orbiter records a pass. With 2 viewpoints, parallax nails down distance, and 3-dimensional structure. Add a second orbiter with a different orbital phase, and suddenly you have stereo vision with depth. The coma becomes a volume you can slice and analyze, not just a flat glow. Think medical imaging, but for a snow cloud that forgot to respect personal space. Even the Martian surface might join the performance indirectly. Wide-angle monitors on landers and rovers keep tabs on the sky for dust and clouds. If the geometry lines up and the atmosphere cooperates, these quiet watchers may spot a subtle brightening, a ghostly streak, or a change in background glow as material gently brushes the very top of the air. No promises. Mars is photogenic but fussy. But even a null result tells us that any incoming dust stream was thin enough to slip by unnoticed. Science loves a clean silence, almost as much as a spectacular shout. Engineers, meanwhile, have their own checklist. A dusty comet tail can be harmless at vast distance and still prompt caution. Operators might roll a spacecraft to present smaller profiles during the highest risk window, or pause sensitive observations while the environment is noisy. Protective postures are part of the ballet. Do the science, keep the hardware healthy, write the report, live to do it again. It is the orbital version of wearing safety goggles that also happen to record high-definition video. Functional fashion. If the cosmos is in a generous mood, we may even catch an occultation, where the comet's coma glides in front of a background star. As the star's light dims and returns, instruments infer how dense and clumpy the gas and dust are along that tiny line. Multiple occultations at different distances from the nucleus sketch a profile of the coma that models alone cannot match. It is the oldest trick in observation. Let a steady lamp shine through a cloud and watch what the cloud steals. However the show plays out, Mars's balcony changes the narrative from a single auditorium view to a theater in the round. We trade flat paths for volumes, static portraits for time-lapse, and when the datasets sit side by side, Earth's long watch, Mars's close choreography, we get a layered story worthy of replay. Next, we will look up from instruments to skies and ask what a world with thin air might actually see. The odds of flickers, streaks, and whispers of meteors tracing the red dusk as the visitors' crumbs drift by. Chapter 14. Dust and Sky Shows. Could Mars see a meteor show? Maybe a whisper, not a roar. If dust grains cross Mars's path at the right moment, they might graze the atmosphere and burn briefly. Mars's air is thin, so fireworks would be more like static than a stadium concert. Still, a rover selfie with a faint streak in the sky would break the internet faster than a cat riding a robot vacuum. Begin with the stuff itself. A comet sheds a zoo of grains, frost dust the size of smoke, gritty specks like beach sand, and the occasional overconfident pebble. The tiniest float away on sunlight's shove and never come close to any world. The mid-sized crowd meanders along with the nucleus's path for a while before spreading into a loose ribbon. The lumbering few stay near the parent's lane like shy parade balloons. If that ribbon crosses above a planet, you have a chance at skywriting. On Mars, chance is the key word. The ribbon must clip the planet's address at exactly the hour the world happens to be under it. Cosmic scheduling remains a tough boss. Now picture Mars's sky as a quiet theater. The air is thin, the stage lights are dim, and most nights the dust in the atmosphere gives the sunset a rusty glow that lingers. To make a meteor, a grain must slam into that thin air so fast that the air in front of it cannot get out of the way. The grain's surface heats, molecules break apart, and a tiny envelope of gas around it begins to shine. On Earth, that glow can grow loud because the air is thick and the breaking is abrupt. On Mars, the same grain coasts farther before it gives up enough energy to light the scene. The show is stretched, muted, and higher up. Less cymbal crash, more brushed snare. Speed matters, and comet dust has plenty. Even a speck can hit the air faster than a jet crosses a continent. But size sets the brightness. A smoke-sized particle warms and cools quickly and may never get bright enough to poke through the natural haze. A sand grain has a better shot. A pebble is ambitious, but ambition meets reality when gravity is modest and the air is a whisper. Many pebbles will skid through the upper atmosphere and head back to space, leaving only a faint signature behind. Mars is the cosmic bouncer who checks your ID and then shrugs. Not tonight, friend. There is also the question of color. On Earth, different metals in dust grains paint meteors with quick hints of green or orange. On Mars, the palette would lean toward pale lines and soft flashes because the thin air favors a shorter, quieter burn. Add in that the sky background at night can be dust bright, and you see why spotting these traces is hard. The best chances come when the sky is crisp after a calm day. The sun is well below the horizon, and the geometry of the incoming stream puts the glowing segment in a darker wedge of the dome. You could call it meteor yoga. Breathe, wait, align. What about the ground crew? Landers and rovers carry wide-angle eyes that watch the sky for weather and for occasional glints. With careful planning, they can be set to take repeated short exposures across a likely radiant, the point in the sky where the streaks seem to diverge. Even then, detections would be coy, thin lines a few pixels wide, sometimes so faint that only stacking many images reveals the trail. A rover could also look for the briefest of sky brightenings, a general soft lift rather than a sharp streak. If many fine grains arrive at once, it would be the meteor equivalent of white noise, a hiss barely above the hiss of the camera itself. Orbiters have another angle, a camera looking across the limb of the planet, with black space as the backdrop, can tease out delicate streaks that would drown against the face of the planet. If they catch a path glowing along the limb, analysts can measure how high the action is and how long it lasts. That height hints at how dense the air was where the grain did its work, which in turn points to the grain's energy. From one faint line, a whole small detective story spills out. Size, speed, even whether the grain was fluffy like soot or compact like glass. Meteor smoke, the ghostly residue of ablated material, might also have a role. On Earth, such smoke can seed thin clouds high above the weather. On Mars, any smoke would be rarer and more ephemeral, but in principle it could contribute a whisper to the haze for a short time. Detecting that would require instruments tuned to very specific wavelengths and patient comparisons before and after the encounter. It is not the sort of thing that wins headlines, but it is the kind of note that brightens a scientist's week. Could any dust actually reach the ground? A hardy few might, but not as fiery visitors. Without thick air to flash them into light and ash them to nothing, some sturdy fragments could decelerate gently and settle as unassuming grains among the native dust. If someone were to brush a rover's deck the next morning with a tiny broom, they would not know which speck crossed interplanetary space and which rode up on the last whirl of a local dust devil. Space does not label its confetti. There is a charming possibility of meteor-induced glows higher up, where the incoming grains ionize a moving band of air and tickle it into a brief blush. If that happens, an ultraviolet or visible emissions spectrograph could catch a thin, shifting ribbon that sweeps across the sky map, quick as a whispered joke. The ribbon would not be bright. It would be clever. Mars specializes in that kind of show. And yes, there is the dream of a rover selfie with a streak. The practical version looks like this: a fixed tripod, a long sequence of short exposures, a lot of patience and luck. The streak would be faint and probably small, yet a single frame with a sliver of light arcing above the ridgeline of a dusty crater would say more than any chart. It would be a postcard from a world that, even in its quiet, finds ways to surprise. So, could Mars see a meteor show? Think subtle. Think a poet's reading, not a rock festival. If the ribbon of dust and the clock of orbits conspire, the red planet might blush with a few shy scratches of light, and then go back to being ancient and calm. Next, we step behind the spectacle and treat the tail itself as a laboratory bench, reading its structure to learn about the wind that sculpts it and the grains that build it, one illuminated breath at a time. Chapter 15. The tail is a laboratory. Tails form because sunlight and the solar wind peel material away and sweep it back. The dust tail marks the road the comet has traveled. The ion tail points straight away from the sun like a windsock. By tracking both, scientists can reconstruct the invisible weather, learning how charged particles stream through the inner system. It is like reverse engineering the wind by watching one wild dandelion puff. Begin with the two signature features, because they are not just pretty, they are diagnostic tools. The dust tail is the crowd pleaser, broad, golden, and gently curved. It is built from tiny grains that left the nucleus at different moments. Sunlight pushes on these grains with a pressure that cares about size and mass, so each grain drifts at its own pace. The result is a layered ribbon where older, larger grains hang closer to the orbit path, and fresher, smaller grains arc away more strongly. Trace the curves and you read a diary of departure times and grain sizes, a kind of chalk outline of the comet's week-by-week breathing. The ion tail is the minimalist cousin, narrow, bluish, and arrow straight, because ions hitch a ride on the charged wind from the sun. When neutral gas escapes the comet and meets that wind, atoms are stripped of electrons and suddenly feel the magnetic rails embedded in the flow. They sprint down those rails, which means the ion tail faithfully points away from the sun, regardless of where the nucleus is headed. Any kink, twist, or sudden break in this tail is an instant bulletin about conditions in the solar wind. If the wind shifts, the tail swivels. If a shock wave passes, the tail can snap and reform like a flag in a gust. How do we turn these shapes into numbers? Start with simple timing. Take images every few minutes and watch subtle ripples race along the ion tail. The speed of those ripples reveals the speed of the wind itself. See a sudden disconnection. One moment, a continuous streamer, the next, a gap. Then you likely caught a magnetic flip or a shock front brushing past. The gap is not the comet being dramatic. It is magnetic housekeeping in action. By logging when and where these events occur, we map the tempo of space weather without ever touching the wind. Dust tells a slower story, but one that runs deeper into the nucleus. Draw families of curves that represent grains of a single size released at different times. Then overplot families that represent grains of many sizes released at one time. Where the observed tail lies among those families tells you both the size mix and the release schedule. From this, you can infer which parts of the surface were most active on which days, how the activity changed as the comet entered brighter sunshine, and whether short outbursts added extra streams of fine powder. It is detective work with stencils and patience. Light itself adds texture to the lab notes. Polarized light measurements across the dust tail reveal how fluffy the grains are. Fluffy grains scatter light differently from compact grains, so a map of polarization becomes a softness map. Softer, flock-like grains often come from gentle venting. Harder, glacier grains can hint at crust breaking or cliff falls. Meanwhile, colors along the ion tail can pick out different species of ions, letting us watch how chemistry sorts itself inside the flow. A bluer patch might point to one dominant ion. A slightly greener tint could betray another, each responding to sunlight and the wind in its own way. There are side channels too. Some comets reveal an extremely faint sodium tail that fans out close to the sun, a whisper so delicate it takes careful filters to spot. If it appears, its width and brightness track how certain atoms are released and sped up by light alone, independent of the charged wind. That offers a clean yardstick for the push of photons, complementing the magnet-steered ion tail and the size-sorted dust tail. 3 tails, 3 rulers, 1 snowball, doing unpaid internships in 3 departments. Depth comes from geometry. View the tail almost end-on, and you read thickness and internal layering. View it from the side, and you read length and curvature. Stitching these viewpoints together, whether from different times or different locations, turns an airy streamer into a 3-dimensional volume. When you can follow the same knot of dust or the same bright node of ions as it moves, you are effectively doing tomography with starlight, peeling back the layers of the flow as a radiologist would, only with fewer waiting room magazines. Tails also preserve memory. Dust released days ago continues to drift and can be re-illuminated as viewing angles change, revealing echoes of older activity that the nucleus has already forgotten. This allows a kind of archaeological dig within the tail, one stratum for the quiet morning venting, another for the midday surge. a thin lens for that brief outburst near sunset on the nucleus's day. Layer by layer, you reconstruct not only what left, but when, and under what mood of sunshine. Meanwhile, the ion tail records the weather of the wind itself. Smooth when the flow is calm, ragged when turbulence rules, broken when a shock arrives from a solar tantrum. Even the fuzzy border between coma and tail is useful. There, neutral gas becomes ionized, dust starts to decouple from gas, and small electric fields sort particles in subtle ways. A sharp transition hints at strong coupling to the wind. A gradual fade suggests a gentler handshake. Instruments that can read very faint light near the nucleus watch this boundary like birders at dawn. The first chirps tell what kind of day it will be. Finally, the laboratory moves with the bell. As the comet recedes from the sun, the ion tail thins and quiets, and the dust tail fattens into a lingering trail that the nucleus leaves behind like breadcrumbs. Months later, the trail marks where the comet once flew, and by measuring how it sags and spreads, you can deduce how sunlight continued to sort grains long after the nucleus had gone. The experiment continues even after the apparatus has left the room. That is efficient science. Tails are spectacle, yes, but they are also instruments built by nature. Rulers for wind speed, protractors for magnetic direction, sieves for grain size, and calendars for activity cycles. Read them well, and you can hear the weather of space in a whisper of blue and gold. Next, we will follow the traveler as it swings past and fades, tracing what changes the close sunlight carves into the nucleus and what scars it carries into the dark beyond. Chapter 16, After the Pass. Post-perihelion, the comet keeps going. No loop, no leash. Its path bends around the sun and then climbs back into deep space, carrying scars from close sunshine and fresh events carved by heat. Somewhere out there, another star's gravity will barely notice this tiny ambassador cruising by. Space is big, understatement of the millennium. The first thing that happens after the hottest part of the journey is not instant winter. Heat lingers beneath the surface like embers under ash. Even as the comet recedes, warmth percolates downward, reaching pockets of ice that slept through the main act. They wake late and blow a few last, stubborn puffs. Post-show encores that keep the coma alive longer than you would guess from the new distance. Activity tapers with a ragged edge, not a hard stop. If you could listen, you would hear a fading hiss, interrupted by the occasional cough when a crust finally surrenders. Those encores write new features on the nucleus. Sun-facing slopes slump, delicate overhangs collapse, the dark blanket of processed dust slides and resettles, sometimes clogging vents, sometimes revealing fresh patches that will be next towards headliners if the object ever revisits sunshine. Think of a campsite the morning after, footprints in the soot, a collapsed ring of stones, and a scorch mark that will take a long time to forget what happened there. Except here, the campsite is rotating, weightless, and absolutely terrible at returning your deposit. Spin rarely survives untouched. Jets that favored one hemisphere on the way in may favor another on the way out, as the orientation changes relative to the dwindling sunlight. Those uneven taps nudge the rotation rate. A slow day can become slower. A fast spinner can pick up a little more pep. The axis can tilt a whisper. A handful of objects even tumble, trading a neat twirl for a wobble that makes the lighting unpredictable, and the activity map a moving target. The choreography looks messy, but the mess carries clues. How mass is distributed inside, where rocky ribs stiffen the shape, whether the body is a single chunk or a handshake between rubble piles. Fragments are the drama no one bets on, but everyone watches for. Near the sun, thermal stresses pry open seams. Outbound, those seams sometimes decide they enjoyed the freedom and widen. A modest piece can peel away and become a companion, tracing a parallel arc for a while before drifting off. Astronomers spot these sidekicks as faint, stubborn points marching near the primary. When they appear, the comet's dust production typically spikes, because newly exposed surfaces cough out their own supply of grains. It is not catastrophic so much as enthusiastic, like a cheer squad that multiplies without asking permission. Meanwhile, the tails evolve from banners to breadcrumbs. The ion tail, powered by the wind of charged particles, thins until it is more suggestion than structure. The dust tail fattens into a trail that remembers where the comet has been. Larger grains, unbothered by light's push, linger closest to the old path. Smaller grains spread into a ghostly fan that a patient telescope can still tease out months later. That lingering trail is a kind of flight recorder. Read how it sags and spreads, and you learn what sizes dominated the outflow, what the release tempo was like, and how quickly light corralled the finest powder. The nucleus itself dims into anonymity. Early images show a charcoal pebble embedded in its own mist. Later, even the mist retires, and you are left with a point of light that looks like a star with stage fright. At that stage, measurements lean on precision. Astrometrists, people who treat positions like fine china, log the object's coordinates night after night to refine the outbound course. Every tiny deviation they squeeze from the data shortens the list of potential futures, sharpening the line along which the comet will exit our neighborhood. Exit does not mean stillness. On the scale of the galaxy, our sun is driving in heavy traffic. The local stellar crowd drifts past. The galactic tide breathes. Clouds of gas and dust drift in lanes you could spend centuries mapping. Through this, the comet sails. It is small compared with the emptiness it crosses, and stubborn compared with the gentle pulls that try to reshape its route. Over ages, those pulls will matter. A far-off star may pass close enough to tweak the heading. A broad, lazy tide may swivel the line of travel a hair. But on any human timescale, this is just a quiet cruise through countryside that never ends. Radiation resumes its long, patient craft. The skin darkens under starlight and cosmic rays. Fresh fractures anneal. Porous foam becomes a little less porous. Volatile ices near the surface retreat deeper, chased by heat that took seasons to arrive and will take seasons more to leave. If you could return in 1,000 years, you might find a surface that looks calmer and harder, like lava that finally admitted it was rock. Time erases graffiti in slow motion. Back at mission control and in backyard observatories, the plot twist is paperwork. With the show fading, scientists compare what was predicted with what happened. Did the jets nudge the path more than expected? Did heat soak deeper than the models said? Were there odd molecules singing louder than they should have? Or grains reflecting light in a way that hinted at unexpected textures? The answers feed new models that will greet the next visitor, because there is always a next visitor, even if we do not know its name yet. In that sense, every comet is both a story and a rehearsal. There is a quiet romance in this fade-out. The comet arrives loud, earns headlines, and as it drifts away, becomes an anonymous traveler again. It will pass the orbits of the outer worlds, stride past the frozen borders where our local comets nap, and keep going until even our sun is a bright memory. Somewhere much later, the tiny body will cross another invisible county line, where someone else's gravity writes the road rules. No brass band will greet it. No banners will fly. And still, a snow-darkened stone will cast a microscopic shadow on space and keep its counsel. That is endurance without ego. We have followed the arc past the spotlight and into the night. But curiosity prefers a fresh stage. Next, we will ask the tempting questions that hover after every farewell. What if we could meet one of these travelers on purpose, take a sample, or even hitch a ride? And what if dust exchanged between stars has quietly been delivering recipes to worlds like ours all along? Chapter 17. What ifs worth asking? What if a future mission launched fast enough to catch an interstellar comet head on? A sample returned from another star's leftovers would be a scientific mic drop. What if interstellar visitors occasionally drop dust on planets, seeding chemistry in new worlds? That is panspermia's cousin, not life hitchhiking, but recipes arriving by mail. Big questions thrive on small grains. Begin with speed, because that is the entry fee. A true outsider barrels through the inner system with the attitude of a marathoner who forgot how to stop. To meet one on purpose, you either leave very early or you leave late and leave fast. Early means stationing a ready-to-pounce spacecraft far from the sun, perched like a lifeguard on the rim. Late and fast means pulling every trick in the book, skimming close to the sun to steal energy from the gravity well, riding boosters that make launch pads sweat, or unfurling sails that drink sunlight for thrust. Laser-pushed sails have also joined the rumor mill. Point a powerful beam at a featherweight craft and let pure momentum do the heavy lifting. If that sounds bold, good. Bold is the price of admission when your target refuses to wait. Detection is the second half of the chase. To catch a visitor upstream, you must spot it while it is still far and faint. That argues for vigilant eyes in cold, dark places. Infrared sentinels far from Earth's heat survey telescopes that sweep sky after sky, and clever software that recognizes the telltale motion of a body that does not fit the family geometry. The moment the alarm rings, pre-planned trajectories take the stage. Imagine a play where the actors do not know their cue until 30 minutes before showtime, and yet they hit the mark anyway. That is interstellar interception. Say we make the meet. What do we bring to the handshake? Proven tools suddenly look like souvenirs worth repurposing. Aerogel collectors, tested by earlier missions, could net dust grains as the spacecraft flies through the coma, preserving delicate structures that would otherwise vaporize. High-resolution mass spectrometers could sniff vapor directly, reading out molecular recipes before sunlight edits them. Microscopes could image grain textures that tell stories about slow growth in cold, dark clouds versus sudden shocks near a youthful star. A drill would be a fantasy, but a fast flyby rarely leaves time to land and sip tea. Think food truck tasting menu, not full banquet. Sample return, though. That is the audacious dream. Bottle a few milligrams of dust, stash them in a shielded capsule, and bring them home. Laboratories on Earth can do miracles with crumbs, isotopic ratios that reveal the climate of formation, chiral preferences that hint at the history of light bathing the dust, and molecular family trees that show whether complex organics assembled on grain surfaces or in hidden pockets of ice. If the analysis shouts different from local, every model of planet formation gets a fresh coat of paint. If the analysis whispers familiar but with a twist, we learn that the galaxy favors certain recipes. And our solar system is not a quirky chef, it is a reliable diner. Now the second what if, postal chemistry. Even without headline comets, interstellar dust threads the galaxy. Most grains are harmless drifters, but a visitor with a generous coma can sprinkle a planet's upper skies with organics and minerals that act like seasoning. No, not life itself, just the pantry items that life, given patience and puddles, can work with. On a young world, a steady drizzle of such grains could shift the starting conditions for prebiotic chemistry, the way a pinch of salt can rescue a soup. The idea sits between poetry and lab bench, plausible, testable, and charmingly stubborn. How would we test it? First, by cataloging the inventory of organics in different visitors and comparing them with the micrometeorites that gently land on Earth each year. Do we see the same families of molecules? Are there isotopic signatures telling us they were baked under a different lamp? Second, by monitoring atmospheres during close comet passages. If a planet's upper air shows an uptick of certain radicals or fragments that match the visitor's breath, that is circumstantial evidence that delivery works. Third, by experimenting on the ground. Expose mixtures of comet-like ices and dust to radiation and gentle heat. Then watch them assemble more complex compounds. Chemistry loves a good montage. There are caution flags, and they deserve front row seats. Planetary protection is not only about keeping worlds safe from our germs, it is about keeping our samples safe from world germs. Return capsules must be secure enough that what we bring back is what we found, not what we picked up along the way. Ethical questions ride shotgun. If one day we explore a living world, the last thing we want is to confuse native molecules with imported snacks. Scientific mic drops are great. Scientific facepalms are forever. Engineering brings more reality checks. Interceptors must survive dust hits at brutal relative speeds. Shields of layered material, Whipple style, can turn lethal pebbles into harmless fluff. But weight is money, and missions love to diet. Communications lag increases as we sprint outward, so autonomy becomes more than a buzzword. The spacecraft must decide in seconds whether to tweak its aim, change exposure times, or protect itself during a surprise outburst. The best mix is a brainy probe with a clear checklist and the confidence to improvise when the snowball sneezes. If all the hurdles clear, the payoff is cultural as much as scientific. For the first time, humanity would hold in gloved hands a pinch of matter that never belonged to our sun. That pinch carries a rumor from a distant nursery. This is how rocks and ices began over there. Whether the rumor matches our story or not, we win. Either we discover that nature writes similar recipes across the spiral arms, or we discover that diversity starts at the ingredient list. Both answers make our corner of the universe feel less provincial. And the dust delivery idea? Even a small confirmation would be a plot twist worthy of a campfire. It says worlds are not sealed boxes. They are open kitchens. They trade spices on the slowest mail route imaginable. It is not life flying coach. It is the cookbook arriving in dog-eared pages. We have played with maybes and built castles of careful optimism. Next, we land the plane. In the closing chapter, we will tie the threads. The sun's curve, the geometry's timing, the giant's distant nudge, and the comet's own fidgeting, and we will leave with a simple truth dressed in starlight. Cosmic clockwork needs no drama to be beautiful. Chapter 18, the point of the story. So what is drawing 3I/Atlas toward Mars? Start with the sun's gravity, add geometry, sprinkle in distant nudges from giant planets, and finish with the comet's own feisty jets and the push of sunlight. The result is a one-time crossing that just happens to graze Mars's lane while the cameras are rolling. No conspiracy, just exquisite clockwork. Space is not trying to impress us, but wow, does it deliver. In our next chapter, we will chase the chemistry, what the colors of a comet's light reveal about the kitchen where it was baked, and how that recipe compares to the ingredients that built our oceans and rocks. And you, to tie the threads, imagine a silent orchestra tuning up. The deepest instrument is the star's pull, steady and unfussy, laying down the bass line that everything else must follow. Over that, the melodies of motion, angles, timing, and three-dimensional paths interweave and set where phrases meet. Far in the background, the big planets contribute quiet harmonies that shift the key a half step here and there. Then come the small percussion hits, puffs from vents, flicks from light, breezes of charged particles. None of these parts alone makes the concert. Together, they play a passage so tight it looks choreographed by intention. It is not. It is what happens when rules are dependable and time is patient. Humans, of course, adore intentions. We like agents and aims. A comet, leaning toward Mars, reads like a plot point, the kind of thing a novelist plants in chapter 1 to pay off later with a twist. But the cosmos writes with algorithms, not foreshadowing. The star curves the playing field. The traveler follows the slope. The planets show up when their calendars demand. The surface of the visitor hisses where warmth finds a tunnel. The result feels authored only because our pattern detector is very proud of itself. It is the same brain that sees pictures in clouds and manages to find its phone in a messy room. Useful? Absolutely. But when we point it at the sky, we have to add humility. Not every near overlap is a romance. Sometimes it is just two lines doing their jobs at the same moment. What makes this particular moment worth our applause is not that Mars was chosen, but that the precision was inevitable. Consider how many things had to agree without speaking. the star's mass and the comet's inbound speed, the tilt of the path and the distances between rings of worlds, the slow, old choreography of giant planets setting the general traffic flow, the tiny, recent tugs from outgassing, shifting the arrival by a sliver of a day. It is a towering stack of causes, each one ordinary on its own, that yields a spectacle we cannot help but call special. Nature is very good at making the mundane add up to the marvelous. Your morning coffee proves this daily. There is also a kind of democratic beauty in the outcome. No one gets top billing forever. Another year, a different world will be in the spotlight. Another visitor will tilt a different way. The script will rhyme, but it will not repeat. That is the pleasure of orbital mechanics. You can know the law and still be surprised by the scene. It is like learning the rules of chess and then watching someone invent a new opening you have never seen. Same board, same pieces, fresh gasp. From our vantage, the payoff is twofold. First, we get data that reaches across disciplines, motion to test models, light to test chemistry, plasma to test space weather, and images to test our patience while we wait for downloads. Second, we get perspective. A single traveler from elsewhere swings through, and suddenly our own neighborhood looks different. Angles sharper, shadows more informative, distances transformed from abstractions to landmarks. Curiosity can be a mirror. Sometimes the thing we learn most about is ourselves. We should be honest about uncertainty too, because that is where discovery lives. Predictions tightened with each night of observation, but they never became a prophecy carved in stone. Small pushes kept scribbling in the margins of our ephemerides, and we edited with erasers ready. That is not a flaw, it is the method. Science thrives on shrinking error bars, not on pretending they never existed. If the universe is a clock, it is one that lets you open the back and watch the gears, then tucks a few extra cogs under the springs just to see if you are paying attention. A word about awe, because it sneaks in even when we are being all sensible and spreadsheety. Awe is not the enemy of understanding. It is the fuel that gets you to the lab on a cold morning. Knowing that sunlight can nudge dust and that angles make meetings inevitable does not make the tale less lovely or the timing less delicious. If anything, the elegance underneath the show is why the show lands. The cosmos is the rare performer who explains the trick and still gets a standing ovation. So the point of the story, a traveler from another star will skim the realm of Mars, not because of secret invitations or planetary flirting, but because gravity sculpts, geometry schedules, far giants adjust, and icy vents fuss. 4 ingredients, baked by time, served as a chance alignment our cameras can enjoy. We did not summon it. We simply had the good taste to notice. Next time, we switch from choreography to cuisine. We will read the colors of a comet's glow like spice labels, trace the pantry where its ices first formed, and compare those flavors with the recipe that built seas and stone and the chemistry inside you. Bring your curiosity and your metaphorical apron. The kitchen lights are on.